So, hello Year 12 and welcome to the last topic on this side of the course that we're going to cover, and that is Group 2. It was a very short course, curtailed obviously by coronavirus, so you haven't had a test on this yet, and I'm not sure whether you managed to get through all of the information, so we'll see what you should know about Group 2. So, as usual, here's the spec. You need to understand reasons for the trend in ionisation energy down Group 2. You need to understand reasons for the trend in reactivity down the group. Know the reactions of the elements magnesium to barium in Group 2 with oxygen, chlorine and water. Know the reactions of the oxides of Group 2 elements with water, dilute acids and their hydroxides with dilute acid. Know the trends in solubility of the hydroxides and the sulfates in Group 2. Understand the reasons for the trends in thermal stability. So this is thermal stability of the nitrates and the carbonates of Groups 1 and 2 in terms of the size and charge of the cations involved. Understand the formation of characteristic flame colours by Group 1 and 2 compounds in terms of electron transitions. Students are expected to know the flame colours for Groups 1 and 2 compounds. Okay, a bit of expanded learning there. You started it at GCSE, you had 5 to learn at GCSE, now you need to know them for Group 1 and 2. And understand experimental procedures to show patterns in thermal decomposition of Group 1 and 2 nitrates and carbonates, flame colours, okay? This is really essential. Although these aren't required practicals, they are often examined. They will ask you to design an experiment to show this. Right. As you go down Group 2, what happens? Well, the best thing to do is think back to your GCSE. You know for Group 1 they get more reactive as you go down the group, and Group 2 being right next door is the same. So as you go down Group 2, reactivity increases. Why is that? Well, that's because as you go from beryllium, which is quite small with 2 outer electrons, to something like barium, which is huge with 2 outer electrons, lots more inner shells. You need to talk about outer electrons further from nucleus. The fact that there's a weaker attraction to the nucleus. So they are easier to remove. So it's a faster reaction. Okay, just very similar to what you did at GCSE with the Group 1. Now, of course, you could talk about shielding here. And the fact that there's more shielding for barium as more, barium as more inner electrons. But do make sure you understand what you're talking about if you're going to talk about shielding, because it's very easy to say the wrong thing if you're not really understanding the shielding. As you go down Group 2, the ionisation energy decreases, and that's for the reasons above. Of course, ionisation is removing an electron. It's worth here refreshing your memory that all ionisation energies are positive, because it always takes energy to remove an electron. So it always requires energy to remove an electron. And here we go. Here is a graph showing the first ionisation energies of the group 2 elements. And as you can see, ionisation energy decreases down the group as less energy is required to remove electrons due to more shielding and less attraction to the nucleus. The reactions you need to know, as it said in the spec, are magnesium, calcium, strontium and barium with oxygen, chlorine and water. Do you know these? Well, you know that when you burn magnesium in oxygen, you've seen this many times before. You've seen the blue, you've seen the bright white flame, probably through a blue filter, if your teacher was being very safe. And you should know that it generates the group 2 oxide, so magnesium oxide, for example. State symbols, magnesium solid and oxygen gas going to magnesium oxide solid. Group 2 metals, all of them react readily when burnt in oxygen. Does the group 2 metal react with oxygen at room temperature? Well, if you've ever looked at your magnesium ribbon and seen how pitted and oxidized it is, you will know that yes, that magnesium ribbon is reacting with oxygen at room temperature. It just occurs a lot more slowly. With chlorine, depending on which teacher you had, you may have seen a strip of magnesium dropped into a gas jar of chlorine. Again, just as with the oxygen, it burns very brightly, giving magnesium chloride solid. Hot group 2 metals react readily with chlorine gas. That shouldn't be a surprise to you. This is not a mistake. This M stands for a group 2 metal, which includes but is not limited to magnesium. And when you react a group 2 metal with water, what do you end up with? You end up with the hydroxide, and hidden under here you end up with hydrogen. Okay, and this is akin to the group 1 reactions, again from GCSE. Potassium and water made potassium hydroxide and hydrogen. Sodium and water made sodium hydroxide and hydrogen. Group 2 metals behaving like the group 1 ones. You react them with water, they generate hydrogen. The magnesium, if put in water, reacts very slowly, but you do see bubbles over a matter of minutes to hours forming on the surface of the magnesium as it slowly oxidizes. As you go further down the group, it gets faster. The question is, why have I put solid/aqueous? And that is obviously because, as we'll see a bit later, different group 2 metal hydroxides have different solubilities. Some of them form solids, some of them form solutions. But all group 2 metals react with cold water. As you go down group 2, the reactivity with water increases. And we'll come to the solubility in a second. Let's have a look at the video.
In this video, we will move down group 2 of the periodic table, looking at reactivity. The first metal in group 2 is beryllium, which is highly toxic and unreactive to either water or steam. The next metal down is magnesium. Magnesium reacts very slowly with cold water, but does react with steam, which we can see here. It forms a gas, hydrogen, which
so
can
that
be
equation is wrong, and we'll get to why in a second.
And also the white powder, magnesium hydroxide, which can be seen here.
It's actually magnesium oxide.
After magnesium comes calcium, which does react with cold water, fizzing to produce hydrogen, and also the insoluble calcium hydroxide, which you can see precipitating out of solution here. We can demonstrate the production of calcium hydroxide by putting some calcium in universal indicator solution. As before, hydrogen is produced,
that
giving a
equation is
foam
correct.
at the top of the cylinder. And also, as the alkali calcium hydroxide is produced, we can see that the universal indicator solution gradually turns orange, then green, then blue, showing that the solution has now become alkaline. If we continue down group 2, we find strontium. This has to be stored under oil to stop it being oxidized by the air. The oil on the strontium causes the reaction to begin slowly, but gradually it picks up, and we can see that the strontium is reacting vigorously with the cold water. The bubbles, as ever, are hydrogen gas. You can also see some white particles in the solution. These are the slightly soluble strontium hydroxide. The next metal in the group is barium. This is slightly more reactive than strontium, and the reaction with water looks much the same.
Okay, so if you react magnesium with hot water down here, then you do get magnesium hydroxide and hydrogen, just as you saw in that video with the calcium and water and the strontium and water. However, you get different product if you react magnesium with steam. If you react magnesium with steam, then what you actually get is magnesium oxide, not magnesium hydroxide and hydrogen. And this is just due to an effect of the concentration of the water. If you've got steam, then there's much lower H2O concentration, and thus the chance of two water particles hitting the magnesium during the reaction is much lower. But do watch out for that. Magnesium and steam makes magnesium oxide, whereas all the group 2 metals and water make the hydroxides. Something that you will have known from key stage 3 is the reaction of metal oxides and metal hydroxides with acids. Hopefully it comes as no surprise to you if you react magnesium oxide, a base, and hydrochloric acid. Acid and base makes a salt, magnesium chloride and water. Predict the products and balance. So strontium oxide and sulfuric acid, well, that should make strontium sulfate. Barium oxide and phosphoric acid, that should make barium phosphate. Calcium oxide and ethanoic acid should make calcium ethanoate. So strontium sulfate and water, barium phosphate and water, calcium ethanoate and water. Again, just worth pointing out with the ethanoic acid, you should know by now, but this is the only acidic hydrogen. So that's removed. Calcium ethanoate has this formula with the H removed. So what happens if you put a group 2 oxide in water? Well, if you put a group 2 oxide in water, it gets the chance to react with that extra water molecule, and you end up with the hydroxide. So magnesium oxide solid and water making magnesium hydroxide solid. If you react that magnesium hydroxide with hydrochloric acid, you know by now, acid and hydroxide, salt and water, magnesium chloride and water. All of this should be very, very well ingrained in your mind, having done it since key stage 3. So this is a summarization of all those reactions. The group 2 metal and chlorine makes a metal chloride, and oxygen makes a metal oxide. React that with acid, you get a salt and water. With water is a metal hydroxide, and then with acid you get a salt and water. Okay, all this should be very straightforward. It's basically GCSE. For the solubility, you did an experiment where you looked at whether or not the hydroxides were soluble and whether the sulfates were soluble. And what you should have found was that when you reacted hydroxide with these metal salts, magnesium hydroxide definitely insoluble, and you know that from GCSE, where you use it to diagnose magnesium ions, you get a white precipitate. Calcium, also from GCSE, you would have known, produced a white precipitate. Although calcium hydroxide is clearly sparingly soluble because it is lime water. Strontium and barium hydroxide are soluble. With the sulfates, well, again from GCSE, if I can write, you know that barium sulfate is insoluble. Again, it is one of the tests that you used to diagnose the sulfate. Magnesium sulfate is soluble, so the solubilities they increase down the group for the hydroxides, but they decrease down the group for the sulfates. You do need to know more trends than just the solubilities. You need to know what happens when you heat the group 1 and 2 nitrates and carbonates. And we looked at thermal decomposition. That's when you break down a chemical into simpler chemicals using heat. So thermal decomposition is when a reactant is broken down using heat into more than one product. No other reaction going on, it's just a particular chemical falling apart. This is something you need to know well. I've seen it many times on exam questions. They ask you to describe how you would do an experiment to look at the trend in stability of the group 2 carbonates or the group 2 nitrates. And for the carbonates, you would use this. You would use some sort of Pyrex tube, you would heat it, you would bubble the gas through lime water, and you would time how long it takes for the lime water to go cloudy. Have a think about what variables you need to keep the same. Have a think about why you are adding a certain number of moles of carbonate rather than a certain mass. And these are some sample results. And what you should see for both groups 1 and group 2 is that they get more stable as you go down the group. The reactions, no surprise there, magnesium carbonate forming magnesium oxide and carbon dioxide, lithium carbonate, lithium oxide, carbon dioxide. Balancing should be fairly straightforward there. Now we need to answer why. Why, as you go down group 2, do the carbonates become more thermally stable? Why is the same also true for group 1, such that only lithium carbonate decomposes and the others don't? Well, the reason is all to do with the size of the ion. So if you have a look at beryllium and magnesium, these are small ions with a 2+ charge. Whereas as you go down group 2, you will see that they are bigger ions, but they've got the same charge. That charge is spread out over a larger area. So these down the bottom have a low charge density. What about for group 1? Why is it that only lithium carbonate decomposes? Well, if you have a look here, not only are the ions bigger, but they've also got half the charge. So they have an even lower charge density. So clearly this is something to do with the charge density of the cation. So these are large ions, sodium, potassium and rubidium with a single charge. They have a low charge density. And the fact is that a small ion like magnesium is able to pull the electron density from the carbonate towards one of the oxygens. And this oxygen begins to split off from the rest of the carbonate. So as it says here, this end of the ion is on its way to breaking away and becoming carbon dioxide. Whereas if you've got something massive like the cesium 1+ ion, for example, then you really don't see this same effect, and the electron cloud is much less polarized. So there's no part of it that is trying to break off. So magnesium has a much bigger charge density, so it's able to pull more electrons towards itself more than the large barium or the large group 1s. So this is the carbonate anion with no adjacent cation. And you can see that the electrons are being pulled towards the magnesium, much less so for barium. So group 2 carbonates are more thermally stable as you go down the group. As the cations get bigger, they have less of a polarizing effect. Learn how to describe this. Less of a polarizing effect. And they distort the carbonate ion less. The CO bond is weakened less, so it less easily breaks down, okay? Group 1 carbonates do not decompose with the exception of lithium, as they only have +1 charges. They don't have a big enough charge density to polarize the carbonate ion. Lithium is the exception because the ion is small enough to have a polarizing effect. Just learn how to describe that. The nitrates were quite exciting. You might remember some of them giving off thick clouds of a brown gas eventually. Again, what you would have seen is as you go down group 2, it became harder and harder to break down these nitrates. And as you went down group 1, the nitrates similarly become more stable, okay? So again, as you go down, more stable. These ones release a brown gas. Which is NO2. These ones don't. What's going on? Well, for group 2 and lithium, again, the ion is small enough that it's able to pull the electron density onto one particular oxygen atom, therefore ending up with the metal oxide and nitrous oxide and nitrogen. For the others, though, it's not small enough to pull all the electron density onto a single atom, so instead it pulls the electron density away from the far edge, and you end up with a metal nitrite and oxygen, which is also called a nitrate 3. Okay, so nitrate is often called a nitrate 5, but a nitrite is sometimes called the nitrate 3. The explanation for the change in thermal stability is the same as for carbonates. Magnesium nitrate decomposes easiest because the magnesium ion is smallest. So these are the highlight key points. Smallest, greater charge density, more polarization of the anion, weakens the bond. Okay, so if you can remember those 4 points, you're doing well. Group 1 nitrates do not decompose in the same way as group 2, with the exception of lithium nitrate. They decompose to give a nitrate, 3 salt, and an oxygen. Okay, learn these. Okay, they're not always that easy to generate on the spot, so make sure you can write these equations. So we've got the magnesium nitrate decomposing lithium nitrate and another group 1 nitrate. Final thing, and again this comes from GCSE, where you did something like this, but it's doing a flame test. How do you do a flame test? You need to know the procedures. Dip nichrome or platinum, and you've got to specify nichrome or platinum wire into acid, so hydrochloric acid. To heat to in a roaring blue Bunsen flame to clean. If you want, you can say repeat as necessary. Three, dip wire in acid, then powder. 4, put in roaring flame and observe colour. There are often points available for specifying the type of wire, not ever inoculating loop. Okay, loads of biologists talk about inoculating loops. It's not. You need to talk about nichrome or platinum wire. You need to specify the roaring blue Bunsen flame, and you do need to mention cleaning it with acid. If you do that, you should get the 3 or 4 marks available for the method. The colours you need to know are expanded. Lithium is a sort of deep red. Sodium is orange or orange yellow. Okay, potassium is lilac, rubidium is a red colour, cesium gives a sort of blue flame, magnesium and indeed beryllium give no colour. Okay, so don't get confused about burning the magnesium where you get that bright white light. Magnesium and beryllium do not give a colour in a flame test. Calcium is obviously brick red, sometimes described as orange red. Strontium is crimson and barium is apple green, and you do need to know these. I wouldn't say it was essential you know the difference between scarlet and crimson, but the rest of it you should know those colours. A very frequent question, I don't know why it's asked so often, is where do these colours come from? Well, it comes from the fact that an electron can be promoted to a higher energy level by absorbing either light or, in the case of a flame test, heat. So the electron jumps up to a new energy level. Then this is unstable, and once it cools down, that electron drops back down from the higher energy level, and in doing so it emits a photon of light. Now, atoms can only absorb and emit photons that exactly match an energy jump, and therefore each different element will give out a different colour of light. Looking at 2 examples, if you look at sodium, then heat will promote an electron from the 3s orbital up to the 3p orbital. And when it drops back down to what's called the ground state, the difference in energy corresponds to light at 589 nanometers, which is an orange light. And this is why sodium gives out a very strong orange colour. Magnesium, if an electron is promoted from the 3s to the 3p orbital, when it drops back down from the 3p to the 3s, the difference in energy corresponds to light at 285 nanometers. This is in the ultraviolet, and this is why it does not give a visible colour in a flame test. Okay, that was a whistle-stop tour, actually longer than I expected, of the Group 2 material. Make sure you do know it, it's asked quite regularly. Your homework this week is slightly different. You need to go onto the Google Classroom, which I asked you to join up last week, and there are 48 marks available of exam questions. I would like you to do your best to answer all of those. For a couple of the questions, you will need to upload photos of your work. My intention is to mark every single one of them over the next week. So I will know whether you've done it or not, and I will be passing that information on. Otherwise, there'll be another lesson later on this week, which will probably be some multiple choice questions on Group 2. Have a nice week.